So welcome back. So today I will discuss the single phase AC supply is given to RLC series circuit. So I am applying a sinusoidal voltage to the RLC series circuit. So during positive of cycle of the supply voltage, and this X terminal is positive and negative, and during negative of cycle X terminal is negative and Y terminal is positive, and this is a phase and neutral. The current flows through R is called the IR bar. During positive of cycle, I am representing the directions. The current flows through L is IL bar, and the current flows through C is IC bar. So which will produce a drop, that is VR bar, and this is VL bar, and this one is VC bar. So in a series, the current is same. I bar is equal to IR bar is equal to IL bar is equal to IC bar. In series the current is same, that's why I am taking the current is the reference. I bar is equal to IR bar is equal to IL bar is equal to IC bar. So with respect to current IR, the resistive voltage VR is an in-phase component. VR is an in-phase component. With respect to inductive current, the inductor voltage is leading at an angle of 90 degrees, and with respect to capacitive current, the capacitive voltage is lagging by 90 degrees. So with respect to voltage, the inductive current is lagging. If I am taking the current as a reference, the voltage is leading, and if I am taking the with respect to voltage, capacitor voltage, the capacitor current is leading. If I am taking the reference as the current, and the voltage across the capacitor is lagging. So this condition I am applying. See, with respect to IL, VL is leading. With respect to IC, VC is lagging. So here we are having a three vectors at three phases. How can we add at three phases? So it is impossible. Convert into two phasors, then only we can add by using a parallelogram concept. So I will take one example: 2 plus 3i minus 2i. The complexes will be subtracted, the resultant will be 2 plus i. If a 2 plus 3i minus 4i, and the resultant will be 2 minus i. If a 2 plus 3i minus 3i, it is equal, and the value is only 2. So this condition same I am applying here, and these are the imaginary on the imaginary axis, VL and VC. Now case 1, if VL is greater than VC, now what is the Phasor diagram? So this is VR bar, VL and VC. The VL minus VC is in the upward direction. This is VL minus VC. Now you add these two vectors. So a dry line which is parallel to VR, dry line which is parallel to VR, and dry line which is parallel to VL minus VC. Then I am getting the resultant voltage, and the angle with the resultant voltage and the current is called the power factor angle. So phi is the angle between the resultant voltage and current. From this we are getting the voltage triangle is like this. The base component is VR, and hypotenuse is V, and this value is V, and this is VL minus VC. See here, that means I am getting the positive imaginary axis, 2 plus 3i minus 2i, that is 2 plus i. If this XL or VL, suppose if it is VL, this is VC, EL is greater than VC, then I am getting it as a positive. So now V can be written as VR plus VL minus VC bar. VL minus VC bar, or VR plus VL is equal to I into XL at an angle of 90 degrees. VC is equal to I into XC at an angle of 90 degrees. So VR plus I, if you take a I common, jxl minus jxc. So VR is I into R plus j times of I into xl minus xc. J times of I into xl minus xc. So I can be written as I into z. I will be cancelled. Then z is equal to R plus j times of xl minus xc. From this we are getting the voltage triangle, impedance triangle. V is equal to VR plus j. Why I am directly writing means it is in the positive axis. VL minus VC. So from this I can calculate the magnitude of the voltage under root of VR square plus VL minus VC whole square, and the angle tan inverse of imaginary part VL minus VC by real part VR. So I can represent the impedance triangle. So the horizontal is R and the vertical portion is XL minus XC and this portion is Z, and the magnitude of the Z is equal to under root of R square plus XL minus XC whole square, and the angle is tan inverse of XL minus XC divided by R. So again the same story, voltage triangle, and this one is impedance triangle. If you multiply I to the voltage triangle, this is VR, VL minus VC, and this is V. Multiply I to the voltage triangle, then I am getting the power triangle. So this power is called the complex power, and this power is called the QL minus QC, where QL is equal to VL into I, QC is equal to VC into I, and this is the active power. So power is equal to VR into I, and as we know from this cos phi is equal to VR by V, and VR is equal to V cos phi. So substitute here, then I got it as VI cos phi. The units of active power is watts, and S is equal to VI, that is okay, and reactive power QL minus QC is equal to VI sin phi. So sin phi is equal to, from this sin phi is equal to VL minus VC by V, and as I am getting here VL minus VC into I, so substitute that VL minus VC is equal to V sin phi, so VI sin phi, and the complex power is equal to VI. So coming to the impedance triangle, and this one is R, vertical component is XL minus XC, and this is impedance multiplied I square with all the terms, then this is active power, net reactive power is QL minus QC, and the complex power is I square Z, and this is a diagram, and this case 2 is VL is less than VC, that is 2 plus 3I minus 4I, I am getting the resultant is 2 minus I. So this one is I, voltage VR is in phase VL, and the VC length will be more, that VL minus VC is in the downward direction, or VC minus VL, this is VL minus VC is in the downward direction, or VC minus VL. Why? Because VC, from this VC I am subtracting this means 2 minus of 4I minus 3I, I can write it as. So if this term is negative, VC minus VL, okay, right, add these two, then I will get the resultant voltage. The angle to these two is phase angle. From this I am getting the voltage triangle, the base component is VR, and vertical component is VC minus VL, and hypotenuse is V. And power factor, this is a power factor angle, cos phi is equal to VR by V, and from this VR is equal to V cos phi, and sin phi is equal to VC minus VL by V. VC minus VL is equal to V sin phi. VC minus VL is equal to V sin phi. After that, so write the equation V is equal to VR minus of J times, why? Because it is in the negative imaginary axis, VC minus VL. Yes, is it satisfied or not? See here, 2 minus of 4i minus 3ai, then I will definitely get the negative value only. This is L. Magnitude of V is equal to under root of VR square plus VC minus VL whole square. That phi is equal to tan inverse of minus of VC minus VL divided by VR, negative value. And again I am getting the impedance triangle. So impedance triangle is like this. VR is equal to I into R, this is I into Z, then I into XC minus XL. So I is cancelled, then R, XC minus XL, and this is Z. Z is equal to R minus of J times of XC minus XL. The magnitude of Z is under root of R square plus XC minus XL whole square, and the magnitude phase angle is tan inverse of imaginary part minus of XC minus XL divided by R. Similarly, you will get a power triangle. So active power is equal to VI cos phi, reactive power is equal to VI sin phi, and the apparent power under root of P square plus Q square, that is VI. And the net reactive power is like this. Q net, now it is QC minus QL, whereas is equal to P minus JQ net, because it is in the negative imaginary axis. And the third one, case 3, VL is equal to VC. The voltage across the inductor is equal to voltage across the capacitor. Then I into XL is equal to I into XC, where XL is equal to XC. This condition is called the resonance condition. XL is equal to 2 pi FL is equal to 1 by 2 pi FC. L is equal to 1 by F is equal to F square is equal to 1 by 4 pi square LC, where FR is the resonant frequency, 1 by 2 pi root LC. This is a case 3 condition.